You guys, let's actually go back, I should say, not start. Go back to the basics. In other words, going back to the definition of what I have for my hyperbolic functions, technically speaking, I've only defined the first two. Now, when it comes to the remaining hyperbolic functions, I don't typically define them in the same way I did with hyperbolic sines and cosines. I just cheat and try to mimic the identities you and I have with our circular functions. For example, I would just make a man-made definition or proclaim the hyperbolic tangent of x is the ratio of these two hyperbolics. I will make a proclamation that the hyperbolic secant of x is just simply the reciprocal of the hyperbolic cosine. And you know where I'm going with this. Same thing with the hyperbolic cosecant. Same with the hyperbolic cotangent. It's just, I think, a lot more falls out. Now, I verified for you guys last time that this particular identity holds. I have to confess. We're going to dive in and try to evaluate the hyperbolic sign of one input plus another, just using these two definitions. If you guys just manipulate them, you get something very similar to what you had before with your circular functions. Your addition angle identity kind of looks like this. Likewise, I even have a version for the cosine function, namely the hyperbolic cosine of the sum of two inputs is equal to the hyperbolic cosine of the first times the hyperbolic sine of the second. Unlike with circular functions, I get a plus, not minus. Hyperbolic sine of the first times the hyperbolic sine of the second. Do you guys mind if I stop? Now from this, I can easily derive out of thin air my double angle identities for hyperbolics, maybe half angle identities, and I can just generate a whole series of identities like you and I had before with circular functions. There's going to be some sign changes along the way. After all, you and I saw last time that whether we differentiate a hyperbolic cosine or a hyperbolic sine, we did not get a sign change in either one of them. You can see that immediately from up here, like you and I flipped that last time in class. But you guys, I'm kind of nervous about my differentiation rules. I don't think I'm finished. I mean, if this is how I'm going to define my hyperbolic tangent of x, then I need to differentiate with respect to x my hyperbolic tangent of x. Got a feel for what's going to happen? Anybody? Yeah, I think mimicking like we have with our circular functions, you're simply going to get the square of the hyperbolic secant of x. How would you prove that? You know what? I could. That works just fine. I was thinking maybe you're going to take this one step further and say, be lazy. Let me just use this. You could, but I think life would be a lot easier just stay here. And you find that it varies to be 1 over our hyperbolic cosine squared, which is nothing more than this by definition. I'm just saying you don't have to go that far, but you could. You could. When it comes to the derivatives, for example, of hyperbolic secant, hyperbolic cosecant, which I can't spell apparently, hyperbolic cotangent. Just like you would have expected back with your circular functions, here's what you generate. This product. This product. And this product. It's just that with the last remaining derivatives, actually you do get a sign change. But again, I'm going to rederive these the typical way I would derive the derivatives with the circular functions. I'll just differentiate the reciprocal, the hyperbolic cosine of x, and now pops your derivatives. Excuse me, however, excuse me, when it comes to your inverse hyperbolics, you guys, this is one that I think is extremely useful. Maybe more so than these two. maybe an algebraic expression for the output of the inverse hyperbolic tangent of x. But you guys, this one, since what I'm saying is accurate, that it pops up enough, can I stall? Can I derive out of thin air what this really is? I mean, it's important enough, I think. So for me to generate, algebraically speaking, no calculus, the inverse of my hyperbolic tangent function, let me go back to my definition over there. Let's consider y being equal to the inverse. Excuse me, I misspoke. Y being equal to the, not inverse, but the hyperbolic tangent of x. Let me interchange variables. It's my mathy approach for generating inverse functions. Interchanging variables, I get that x is equal to the hyperbolic tangent of y. And I maintain if I can solve for y in terms of x, that I've generated the output of the inverse hyperbolic tangent function. So you guys just watch me, you relax, I'll do all the work. Shoot, my definition over there is this. This time, diving in deeper into my definitions. I guess that means x is equal to, let's go over there for definition of hyperbolic sine. Wouldn't that just be this? And definition of hyperbolic cosine, that'd be this. Well, I lied a little bit. I forgot to divide by 2, but I get some cancellation, no big deal. But remember, at this stage of the game, it's my mathematical responsibility to dive in there and actually solve for y in terms of x. So, let me give it a shot. I'll multiply both sides of the denominator to get rid of my fractions. And I'll get rid of parentheses. Did you guys catch what I just said to get rid of fractions?
Multiply both sides with the denominator.
Yeah, did I do that?
Yeah.
Completely?
Yeah.
Did I get rid of all the fractions?
No, you still have the negative y.
Yeah, technically speaking, there's still fractions, so if you guys don't mind, I'm going to continue to multiply both sides by something, namely e to the y, to get rid of all the remaining fractions. I think that leaves me with this. And again, remember what I'm trying to accomplish. I'm trying to solve for y in terms of x. I see a couple terms that do involve y. I see a couple terms that do not involve the variable y. So I'll bring all the terms involving the variable y to one side. All the terms not involving the y variable, bring all the terms not involving the variable y to the other side. Oh shoot, you guys, this isn't working. I see y's too many times. I like to see y only once. How can I accomplish that algebra?
You can factor out.
Pull out the dark factor. And I think that leaves you with e to the y. Excuse me, I misspoke, sorry. I meant e to the 2y times 1 minus x being equal to 1 plus x. But that means e to the 2y is equal to its ratio. But that means 2y is equal to the natural log of the ratio. And that suggests y itself is equal to 1/2 natural log of the ratio of the sum to this difference. Let me make the proclamation. I maintain the inverse hyperbolic tangent of x could be expressed as 1/2 natural log of this ratio. But you guys, this does pop up. Maybe you can't see it yet. It does pop up enough with the integration process, particularly when you see me differentiate these hyperbolics. I didn't need all these checks. That was a check for grouping. Let me continue my checks. See what happened if I differentiated with respect to x my inverse hyperbolic cosine of x. Any ideas how I'm going to do this? David?
I was going to say, isn't it the same thing as the regular cosine inverse with the sign change?
Unfortunately, dramatically not.
Of course not.
Well, I take that back. I shouldn't say dramatically. The way I get there is dramatically different,
Okay.
I think. I think to differentiate inverse hyperbolic cosine, why don't you just go to our natural log definition of it, or a natural log interpretation of it, and differentiate there. So I maintain, you guys, am I walking too fast? Can I steal the middle board? Okay, I maintain to differentiate then, with respect to x, the inverse hyperbolic, what did I say, cosine?
Yeah.
I don't care which one I do. I'm just going to differentiate with respect to x, this natural log business. In this case, it was x plus square root of x squared minus 1. So let's do it.
Chain rule.
Did I do it?
Chain rule.
Oh, I missed a chain rule. Actually, the chain rule says multiply by the derivative of what's downstairs, but that'll just be this. Yeah, I am. I mean, there really should be a factor 2 downstairs, but with the chain rule again, to multiply by the derivative underneath the square root symbol, I get a 2x. And the 2's cancel. And I maintain what you see standing in front of me isn't nearly as complex as it looks. I think I've got 1 over something in purple times something else, which is multi-term. But if I rewrote this as a single term by adding or combining fractions, wouldn't I get this denominator as a common denominator? But would my numerator be this? Did you guys see the point behind the color? Complete cancellation, I think in the end, all I'm really left with is a ratio of 1 to the square root of x squared minus 1. So I maintain, to differentiate inverse hyperbolic cosine, I merely get 1 over the square root of x squared minus 1. And I think to differentiate with respect to x, inverse hyperbolic sine of x, is just as easy. It's exactly the same process. I just get a sign change in the radicand position. I still get the same kind of cancellation, but I'm merely left with the ratio of 1 to square root of x squared plus 1.
So wouldn't you want to rationalize the denominator?
You know, it just becomes too nasty at this point. If I did Bradley, I get this. I just don't think it looks better.
Okay.
Besides that, with some of the integrals you've been dealing with so far, you can kind of see that sometimes you had integrals of this form, particularly for which you applied the trigonometric substitution.
Okay.
Now it's just that if you have something in this form, you can just immediately rattle off as an inverse hyperbolic sine or cosine, and you can even interpret it in terms of your natural laws. I also insist, however, you guys, that when it comes to differentiating with respect to x, the inverse hyperbolic tangent, I'm sorry to say it this way, it's just too good. So good, let me derive it. I'll derive by doing this, differentiating this. Because to differentiate with respect to x, this business is the same as differentiating with respect to x, my 1/2 natural log ratio of sum to difference. Let's do it. The 1/2 lingers outside. Differentiating natural log of anything is simply going to give me the reciprocal of that thing. It's just that now the chain rule says I got to multiply by the derivative of what the heck I was actually taking the natural log of, but there's a ratio. I'll use a quotient rule. I get what's downstairs times derivative upstairs, which is 1. Minus upstairs times derivative downstairs, oh, that's -1. All over what's downstairs twice. Now I maintain one of these factors upstairs and downstairs is going to cancel. And that leaves me with a 1/2 times the 1 over 1 plus x times something over 1 minus x, which something is I have no clue. Isn't that just 2?
Isn't that just 0 at the top though? Oh no, sorry, that's 2. I didn't see it.
Yeah, just double check.
Yeah, I saw it.
And I think that's merely going to give me this bit of cancellation. What do you think so far? Okay, if you're okay with it then, let's just put this together. I think I can interpret this whole nasty fraction as a single fraction, as nothing more than 1 over the difference of those 2 squares. And so I'm left with a 1 over 1 minus x squared. You guys, the last couple of days in class, we saw this pop up all the time in integrand position. I kept making these silly jokes saying, what's the answer? You can just state it, it's an inverse hyperbolic tangent. And you and I said, oh, okay, we didn't review those. We'll use partial fraction decomposition.
So we could have used that on the quiz.
Even in the quiz that we just covered,
Yeah.
yeah. So from now on, if you end up with an integral like this, if you so choose, you can avoid the partial fraction decomposition. Just state your answer as the inverse hyperbolic tangent of x. And if you don't think it's very pretty, don't worry about it. Rewrite it in terms of natural logs.
Can you give us some practice problems to do at home?
Oh, absolutely. I will.
Is that inverse or inverse hyperbolic tangent of x over 1? I mean, like in the integral you have on the side, if this was 5, would 5 go under that?
You know, you can always avoid what it's going to look like just by making a quick and easy use of to avoid the whole situation. And I'm not giving you any mechanism for memorizing where the constants are going. I just straightforwardly gave you the basic one. Now you can do substitutions and generate more complex versions. Oh, you guys, I suppose I'm missing a few things. Inverse hyperbolic secant, cosecant, inverse hyperbolic tangent. Actually, you don't have to write this down, but what's kind of interesting about this? Derivative inverse hyperbolic cotangent, same thing. Not even a sign change.
Really?
Yeah. So tangent lines are going to remain the same.
But the cosecant and the secant are going to have a sign change.
No, actually, secant and cosecant are more complex. I don't use them very often, but when it comes to differentiating with respect to x, inverse hyperbolic secant, jeepers, now I'm going to put myself on the spot. -1 over x times the square root. 1 minus x squared. And the derivative with respect to x of inverse, I think I'm right, hyperbolic cosecant of x ends up being this nasty. -1, the absolute value of x, times the square root of x squared plus 1. But again, I don't use this often. Well, now that you guys are completely silent, what do you think of me spending time yesterday and today just deriving these basic relationships, but also deriving the differentiation process? And now I can leave it up to you to go backwards. If ever you come across this in an integrand position, you can immediately proclaim its inverse hyperbolic sign. Don't think it looks very pretty. You can make a substitution in terms of natural logs, etc., etc. And I'll build some examples of homework questions on this. And now that I've done that,
Are we set the question for the test?
I can't, because I haven't signed you anymore. You know, once I create a homework set, it'll be fair for this.
But if we see that as an answer, we can
But yeah,
definitely.
if you're okay with everything I said, and you see some things like this in the integrand's position in tomorrow's exam, and you want to exploit all the theory, please, by all means, go for it. I'm not holding it back, I'm just not forcing the issue. And if you were to sit in your chair and say, I don't want to listen to a word he's saying, you can get away with it. You don't have to listen to one word I'm saying, because technically speaking, if you have any of these pieces in the integrand's position, yes or no response. Wouldn't a trig sub work?
Yes.
I mean, it really would. So you're not dead in the water if you didn't know anything about inverse hyperbolics when it comes to the integration process.
So how would we do these with the perfect square, like with our A and stuff?
Yeah, that's what somebody else is asking. I said, I was just saying, I'm not going to generate all that theory from scratch. I'm just maintaining that if you wanted to, you could just make some quick and easy use ups. Just accomplish the same task. Well, you guys, if that is okay. How about, wow, total of 40 minutes left. There's tons of time. We can discuss what I want to do next. You know if I'm pulling out a straight edge is important. If I consider the graph of an arbitrary function, y equals f of x. Gosh, you guys, how does the song go? The song goes, take the interval from A to B, partition it with a regular partition into n subintervals.
What song?
No, I mean, silly. It's just something
Oh,
I've said
okay.
over and over against this math 30, is that we've repeatedly, regularly partitioned an interval from A
Is
to
this
B.
the one written by Math Magic?
Yeah.
Well, you
No,
won't-
math
you won't be
magic
able
is
to
the
say
single from the derivatives.
But I get these subintervals. I'll rename A to be x of naught. Here's my, whoops, I miswrote, excuse me. My x of 1. My x of 2. All the way down to an arbitrary subinterval. How about the I subinterval? All the way down to last subinterval, the nth subinterval. Now I would like a technique for being able to approximate the area curve from A to B. To do that, I can choose a value of x where in each subinterval. How must I choose my value of x to build these approximating rectangles? Anybody? Okay, for the people I saw Math 30 last semester, how do I choose my x into these subintervals?
You go back and read the Math 30 portion of the textbook.
The answer is I choose them any way I darn well please. Did you guys see my point? No pun intended. It doesn't matter how I choose them. I can choose the values of x anywhere in the subinterval to construct the vertical height of the first approximating rectangle, because when I'm done building the sums, I'm going to take the limit as n increases up bound, so who cares how x is chosen? Now I have got to confess, I'm going to take that back if I merely want an approximation. And if I merely want an approximation, I could be more selective in actually choosing my values of x. Here's one way I can do it. Dive in each of those subintervals and be consistent. Choose the left endpoint of each of those subintervals to build the vertical height of those approximating rectangles. I'll call that the left endpoint rule. I could just as easily have gone in there and chosen the right endpoint of each subintervals. I'll call it the right endpoint. I could just have easily gone in there and chosen the midpoint of each of those subintervals. And if I did, I'd refer to that as a midpoint. Or how about if I say this in a slightly more organized fashion? If in each of these subintervals, that's these subintervals right here, that's the ith one, I can choose my x value, I'll call it z sub I, in such a way that it is, look at that, the left endpoint, the right endpoint, or maybe the midpoint of each of those subintervals. I just maintained it's not going to give me a terribly accurate approximation for the area of the curve, as a general rule, if I have a fairly small value for n. I think the midpoint rule sometimes or often seems to be a better approach, but it's still a bit of work. However, notice something interesting in my picture. If I decided to do this, excuse me, in purple, if I came in and actually constructed not a rectangle, but go up to the curve at the left endpoint, the right endpoint, and connect them, I want a yes or no answer. Is that necessarily a rectangle?
It's a trapezoid.
No, it's a trapezoid. I can do it for the second one. I can do it for the last one. Or how about this, better yet? I can build a trapezoid to approximate the area of the curve over the I subinterval as such. And if I did, oops, excuse me, then I think this vertical height right here is just f evaluated here. I think the other vertical height is nothing more than f evaluated at the right endpoint of the I subinterval. And I think this dimension right here is simply the length of one of the subintervals, the I subinterval in this case, but it's the same as the length of any of these subintervals. And each one of them is going to have a length which is the total length from A to B, divided by how many parts I broke it up into. Now, you guys use your high school geometry. Using my high school geometry, I think the area of this ith trapezoid is going to be nothing more than 1/2 to some of its bases. times this horizontal dimension. Let's take a peek at the next trapezoid. Do you think one of the bases would be f evatted x sub I? You guys think about it. I'm not going to draw it. Imagine the next subinterval right here. With the next trapezoid, do you think one of the vertical dimensions is going to be f evatted x sub I?
Yes.
Yeah, I think it is. In fact, I think each one of these vertical dimensions is going to be counted twice when I sum together the area of all these trapezoids, with two exceptions. The last one is only going to count this vertical height once. The first one's only going to count this vertical height once. So if you were trying to find some kind of explicit formula to generate using the trapezoidal rule with n subdivisions, notice how each and every one of these coefficients has a factor 2, or is a factor 2, excuse me, with the exception of the first and last. Or you can do this. Watch my clumsy hands. With all these terms in the middle having a coefficient of 2, break it up into f of x of 1 plus f of x of 1, then f of x of 2 plus f of x of 2, and take half of them and pull them off to the side. What you're going to end up with right here is nothing more than the left endpoint rule. And what you end up with the last end is going to be the right endpoint rule. You could, if you wanted to, if you'd already computed these two, use this particular implicit formula to generate the result of using the trapezoid rule within subdivisions. You know what, you guys, I maintain with each of these techniques, they're clunky, not terribly accurate. But I got time. Since I do have time, I will employ one of them with an example. So, example. Approximate. How about this interval? I'm just making this up out of thin air. How about from 1 to 3, the natural log of x with respect to x using t sub 4. What do I mean by using t sub 4? Using the trapezoidal rule, subdividing the interval from 1 to 3 into 4 sub-intervals. Let's give it a shot. Pictorially speaking, x-axis, y-axis. We know what the graph of this piece looks like. Here's the interval from 1 to, I said 3. I'll subdivide it into 4 sub-intervals. You guys just double-check my arithmetic's okay. Now, instead of wasting your time by having me try to draw these individual trapezoids, let's just use our explicit formula. Our explicit formula says that t sub 4 is exactly equal to my delta x over 2 times my f evatted by x sub naught plus 2 times f evatted x sub 1 plus 2 times f evatted x sub 2 plus 2 times f evatted x sub 3. And finally, plus f evatted x sub 4. You guys, let's just add these together. By the way, according to my picture, what's delta x? Clearly a half. Well, according to my picture, that's how far each of these ticks are on the horizontal x-axis. We'll be lazy. Just compute it by looking at 3 minus 1 divided by 4, which is still 1/2. I think I'm dividing by 2, and inside my parentheses, let's play. Ooh, that's kind of nice, isn't it? Or shall we rewrite? Is that a 1/4 times the natural log of, I don't know. You guys help me with this. Is that a 3 squared over 2 squared? Excuse me. Is that a 2 squared?
Why is it 1/4?
Because I was dividing 1/2 by 2.
Oh, everything you're doing everything inside the ln right now?
Yeah, everything beyond the ln, I'm just combining these individual logs. I'm bringing the 2 upstairs. This 2 upstairs, and rewriting the sum of 2 logs as a log of a product. But that gives me 2 2s. This gives me 2 5s and 2 3s. This simply gives me 1 3. There's a tad bit of cancellation here and here. Actually, there's even more cancellation here and here, and I think this leaves me with 1/4, the natural log of, I have no clue. Is that 75? Somebody panic and say something in English. What does this number represent?
The area under
Does it?
approximate.
Yeah, it approximates the area of the curve using this trapezoidal rule, not like you did last semester, merely only using left or right or midpoint rule. Yes, sir.
Why is that 5/3?
You mean right here?
Yeah.
Sir, I have no idea. I took my glasses off. You guys look. This TIG is 5/. I am so sorry. Can I fix it? Ay, ay, ay. Unfortunately, that means it changes a lot. Maybe not that much. Changes this to a 2 squared. Ah, jeepers. That doesn't cancel. Okay, you guys, he's pointed out I've really blown it. I guess that changed my answer dramatically to 25 times 27/4. Can I give up?
No.
Please.
If you want to.
Well, you guys, that wasn't very smooth, but I have to confess. Check this out. I'm not going to derive these for you. There is a technique for me to identify exactly how good these approximations are. Outside the math classroom door, nobody ever uses approximation techniques, unless they know how accurate they are. And I have to confess, I am coming to class in summer session, not deriving these out of thin air for you. But there is a way we can actually have control over the error in using both the trapezoid and midpoint rule. Notice that, just a glance, don't look at this carefully. Although before we're done today, I will dive into this carefully, I will. But without looking carefully, can you guys see that these two fractions, whatever k is, are the same? The only difference is the denominator, but this one's bigger. That means, well, the midpoint rule is just a bit more accurate than the trapezoid rule.
So then why would you use the trapezoid rule?
I wouldn't. I only used it as my first example because that's one rule you did not see last semester. I just wanted to do something different.
Okay.
Actually, I would use neither of them. Check this thing out. Whatever the heck these symbols represent, notice how I got a factor of 180 downstairs at n raised to the 4th power. Whatever the heck these symbols represent, looks like this might be a much better approximation technique. And it is. It's so important. I give it a name. I call it Simpson's rule. Now, Simpson's rule is a way for you and I to approximate the value of an integral. Just it gets a little closer to the actual value much more rapidly than left, right, mid, or trapezoidal rules. So if you guys don't mind, can I talk about this new rule? It's really slick. I want you to understand what's really going on underneath everything. You take a peek at not the first, but the first 2 sub-intervals. I want to do this. I need more pens. In red, I want to look at these 3 points. F evaluated x of naught, evaluated x of 1, and evaluated x of 2. Are you guys okay with me saying this, be honest? 3 points determine a parabola.
Yes.
Okay. Because the output of a parabola in algebraic form is ax squared plus bx plus c. So if f of x equals ax squared plus bx plus c, and you were to find b1 parabola passing through 3 points, you'd have to find values for a, b, and c, but when you plug in those 3 points, you get 3 equations and those 3 unknowns. However, with my other Christmas color, now when I choose the next 3 points, I'll have to overlap. I can find the best fitting parabola going through those green points, and I maintain finding the area underneath that second parabola in green approximates the area underneath the curve over those 2 subintervals more accurately than my other processes or my other rules up here. And I'll add that to the area underneath the first red parabola, which I think does a better job as a general rule than the other 3 techniques up here. So I think I need to derive what this thing is called Simpson's rule out of thin air. Let me give myself some room. Because I'm lazy. David.
What's the point?
The point is, this is going to be such a better approximation technique for valuing the area underneath the curve.
Really? Better than an integral?
I thought that was the fun of the integral, it was an
Yeah.
absolute.
Oh, I see your point. Yes, in theory. The minute you walk out this classroom door, you'll realize we've lied to you this whole time. You may have had a whole chapter on integration techniques, but most integrals are non-integrable. In other words, I can't dive into these tricks I've given you in chapter 7 or whatever chapter this is. Most integrals are not evaluated using trig subs, U subs, PFBs, Most of them can't be evaluated, period.
Can you give us an example?
I have to, oh, piece of cake, how do you take a stance?
What?
So enough of us. You guys remember the bell-shaped curves? It kind of looks like this. When you guys looked at z-scores, you're basically looking at the area under a portion of this curve or a curve like this, changing coefficients. And basically it looks like this. For me to find the area in this curve from I don't care where to I don't care where, I can't do it by hand. I have to use some kind of approximation techniques. It's non-integrable in closed form. I agree. Then most integrals aren't integrable.
So all this time we've just been looking at special forms?
Absolutely. Very, very special cases. Now don't take it the wrong way. In a lot of applications, some of these integrals that you looked at repeatedly pop up over and over again.
So if it is integrable, integration is the best way to do it?
Well, I would say so only because if I were to use Simpson's rule on an integral that's integrable, then I'm really getting an approximation form.
Okay.
And why not just go through the work and get the exact value?
Okay.
And if you guys don't like Simpson's rule, don't worry about it. Just give me another week. I'll give you a new technique called power series.
How do you identify if something is non-integrable?
Not easily. Not easy, because a lot of times what you're going to do in your chair is you're going to just whittle away at all these different integration techniques. Nothing seems to work. So it's not an easy question to answer. For you right now, the point is there are going to be some integrals where you, whatever technique you have, the techniques you have collectively in your back pocket are not going to be able to value the integral.
Will you ever throw us a question on a test that relies on us to determine whether it's integrable or not?
No, I think it's going beyond the scope of this course.
All right.
Besides, you guys,
So
we've lied to you in other ways. You guys can only integrate if your function is continuous. It doesn't have to be. There's different types of integration processes. You just won't see them until graduate school, if you go to graduate school for mathematics. There's other types of integration techniques. The most immediate one that comes to mind is Lebesgue integration. Of course, it has a French name. Somebody had a question? Yes, sir.
So we should just, when we come across an integral, we should, and outside the class, we should just start with the Simpson rule.
No, I think outside the class, like what Brad was saying, it'd be so much better to be able to get an exact value. I would have chosen to use one of my integration techniques, or at least see if one of my integration techniques in this chapter applies to that particular integral. I think that would be the best approach.
But if we can define the error, can't we just make it like infinitely small and then start with the Simpson rule?
This is a good point. You can choose to use a lot of subintervals to guarantee certain accuracy. I promise before I'm done today, I'll give you an example of that, where at least we identify how many subintervals we need to create. That's a good point, you're right. This summer session, expect this. I'm not going to trick you, saying, here's an integral, and it's not integrable, and I just assumed you'd use Simpson's rule. I would say, here's an integral, use Simpson's rule to approximate it. I might even ask you to do it on an integral that you could integrate so that you can check your answer. So don't expect me to trick you in that sense. Should I say this? I was going to say I lost it. Okay, you guys, give me a few minutes. You relax. I want you to kick back. And I want to talk about integrating underneath the first problem in red. Oh, I don't like where it is. You guys mind if I do this? Can I take everything and slide it, translate it, x sub 1 units to the left?